Lots of material has been presented in the form of videos, threads, spreadsheets, and drawings detailing the bending of sheet metal, to include using a press brake to make an actual box. 3D modeling is an important design and concept tool which will be covered in this video. I use the word reverse engineering because the 3D models came last in the design process. 3D models could have initially been used, however. They take time to create and got kicked to the curb in favor of bending theory, formulas, information threads, graphic solutions, PDF drawings, spreadsheets, and press brake videos. In doing my own research, questions came up about bending sheet metal accurately. I encountered terms like bend allowance, K-factor, setback, neutral axis, flange distance, mold point, and flat layout. These relate mathematically and can be defined in formulas. It helps to understand these terms and how they relate. Most 3D modeling programs like FreeCAD will need a K-factor. There are links in the description to educational material. My shop includes a diacro press brake, which is what I use to bend sheet metal parts. The aluminum project box was a simple part to start making. It ended up with creating a 3D model after the fact. This video being the first in a series covering 3D modeling of a simple sheet metal box consisting of a bottom and fitted top. Bent parts usually start off with a flat layout, bend centers, and subtractive features like notches and holes. It's interesting to see all the details involved to make a simple part. For cross-checking, I created the flat layouts from formulas, graphical renderings, making the part, and finally 3D modeling. The goal was that all these would agree, which they did. The bent part fell within acceptable tolerances. Let's get front of console and explore the 3D models. Okay, I'm on a Dell Precision 7520 mobile laptop workstation. It's got pretty good power. We're in the Manjaro Linux desktop here. So we'll go ahead and bring up FreeCAD. And the goals here are to explore the models, show you how to do a flat layout from those models, get dimensions, and basically that's kind of going to be what we'll cover on this video. Before we get into the models, a couple of things that stymied me with FreeCAD. I'll go through that. The first thing that's important is the version, and I'm on a FreeCAD Link Daily version 2022.111, referred to as Real Thunder. There's links in the description that'll get you to post threads with all kinds of information, access to the models that we're going to open pretty soon, and some very useful information. So definitely explore those links and make sure that you've got the right FreeCAD version, because the old version, V0.20, will have trouble with these models. So make sure you get that squared away. I'm also assuming that you have basic 3D modeling skills and you know your way around FreeCAD reasonably well. So that's that. And the assembly workbench was something that I had a little glitch with. There's some Python modules that will create errors when you open FreeCAD up. So even though the assembly workbench isn't used, go in there and make sure that you install the modules. There's prompts for it. Get all that stuff installed so when you launch FreeCAD, it comes up clean. So that's important to do that. The other thing that you'll need to do is to go into Tools and select Add-on Manager and make sure that you have the sheet metal workbench installed. You'll see it here. It's highlighted in green, indicated installed. So just follow the prompts, click on it, install it. You will get some errors with 404, modules not found, yada yada, down in the information window here. They don't seem to really matter. The final display here is workbench will be installed properly. So I think that's most important. The errors don't seem to mean anything, so there's that going on, but you'll need to do that. And there's something else that's also important that you'll need to do. If we go into Preferences, when you get your sheet metal workbench installed, let's go and find that. So we're going to go out here. Bear with me here. We'll go into sheet metal, and we'll go into preferences. Here it is. Engineering UX mode. Make sure that is enabled. That's very important in order for the sheet metal workbench to work properly. So if you got all that squared away, you're in good shape. Let's go open up the two models. Here's the project box bottom. Again, there's a little glitch with the sheet metal workbench and how it handles faces, and it doesn't mean anything, so just recompute the module and you can close down this window, this report view window. Let's go ahead and open up the box top. Same situation, a little recompute that we need to do, and a warning down here. Just close that down. So here's our two parts. There's the bottom of the box and there's the top of the box, and we can go ahead and just rotate this around and do that. We do the same thing for the top of the box as well. So what we want to do now is go into the model tree and take a look at the spreadsheet. This is a nice feature. You can create a spreadsheet. It's already been done for you in this model, but it creates a one-stop shop place to input all the design parameters of the model. So these are outside dimensions. So we've got the width of the box, the height of the box, the depth of the box, and the component tab, height, material thickness, bend radius, K-factor, chamfer. Regarding the K-factor, which most 3D modeling programs need, I'm not going to get into all the details of that. There are a lot of details about K-factor that is in the post threads, which you can find in the links in the description. So go there and read about K-factor. It's all there. I've added in some computations, bend allowance, also the overall height of the flat layout and the overall width of the flat layout, just so you can get an idea of how big a piece of sheet metal is going to be required to make this part. So let's go in and let's make this box a little wider. Let's make it 200 millimeters. You'll see a recompute. We'll go back to the box and you'll see here it's kind of a funky aspect ratio, but you'll see this box got a lot wider than it was before. Go back into the spreadsheet and we can make the height 300 millimeters. So you can see how this goes, how this works. We can make that box a little deeper. Maybe we'll make it 100 millimeters deep. You can see what's going on here. It's nice. It's parametric. You can change things. This component tab, we can now change that as well. Let's make that 50 millimeters. Got a little bit more space here for components. So that's how that works. I'm going to go back and put these dimensions back. 101.6. That is 4 inches. 152.4. That's 6 inches. Box depth 50.8. That's 2 inches. Tab height 25.4. That's 1 inch. So these dimensions here are in millimeters, and if you want to work in inches, you can do the following. You can go up to the content for each cell, put an equal sign, and put in 25.4 times 6, and you'll get your conversion. So what can be done here, if you want to redo these cells and do this for each of these cells, you'll have to go up to the content to put in your parameter. You can't do it from the cell, you have to go up here, but this allows you to go ahead and work in inches if you want to do it that way. So we'll go back here and we'll put in 152.4, so this all lines up. So the other thing that I learned that is helpful is the recompute. When you get into a model like the box top that has more faces and is a little bit more computationally intensive, the recompute time is going to occur every time you change one of these cells, and that includes the text as well. So it gets a little bit frustrating because you got to wait out the recomputes for every single value. So there's a way around that. What you can do is you can go in here to the project file name and you can click on skip recomputes. So we can go in here and we can, let's make this 150, let's make this 200, and let's make this 60. So you'll notice that these values in the cells didn't change, but they actually are up in the content. You can see it. It says 150 and the cell shows the old value. Same thing for box height, same thing for box width. So that being said, we don't have the recompute. The model's out of date. So we can go back to the model and we can go ahead and uncheck this recompute, and we can go up here and recompute, and you'll see the model, it now goes ahead and recomputes. So that's how you can avoid recomputing every time you change a cell. But just be careful that you don't forget that this has been checked, and then you wonder why you're getting locked out of making dimensional changes. So let's go back in the spreadsheet. Let's reset this. This will be 101.6, 4 inches. This will be 152.4, 6 inches. And this will be 50.8 inches. I'm sorry, 50.8 millimeters, 2 inches, and then we've left this alone. You can see the recompute occur for each cell change. So here's what we started with. So here's our box. And you can also do some dimension checking if you want from this model. So let's take a look at a front view. Blow this up a little bit. And the box is supposed to be 4 inches or 101.6 millimeters wide. So let's check that. So we'll use this linear measure tool and we'll pick up this point and we'll pick up that point. And as expected, the outside dimensions come back as 101.6, 4 inches. That's what we're looking for. So you can measure anything you want on this model this way. And we'll go back to the model view, and that's kind of how that works out. So you can save these, and there's a bunch of things that you can do. With the tasks here, you want to get rid of these dimensions. You go back and clear these dimensions and basically just close that, and then we get back to the model tree. So that's how you can do measurements. So we'll go back to the isometric view, which is this guy here. We'll shrink this down a little bit. So that's that. So let's dive into how we get the flat layout for this model, and we'll work on that. So there's a couple ways to do it. The easiest and quickest way is to use the sketcher, but you can also create a nice drawing with TechDraw, but I'll get into that in another video. So the first thing we need to do is go into the sheet metal workbench and highlight the bottom face here. And we'll go up here and we'll hit the unfold tool. And you got to make sure that you've got your K factor put in here and ANSI checked, which if you use my models, that'll already have been done. So we'll just go ahead and click OK. And we notice two features added in the model tree: unfold, which is the three-dimensional solid, and then we've got the sketch. So we want to look for the sketch. So let's turn off, wink out the model. Let's wink out the unfold solid and then just leave the actual sketch. So we can come back to part design. We can do a top view. We can go ahead and shrink this down a little bit. So there's your flat layout. There's no dimensions on it. Let me comment on this little cutout here. The theoretical model makes this cutout, and it's not really practical when you make this part. You can drill a hole here if you want, or you can cut a slot. I did with a hacksaw blade, which is really simple, and the video that I put out there that actually shows this box being made will actually show how that's done. So this you got to kind of take with a grain of salt. I suppose if you were laser cutting these parts out, this would not be a problem, but if you don't have access to a laser cutter, this is going to be a problem. So we'll just kind of leave that as modeled, but just be aware of that feature there. So here's our flat layout. The next question is, how do we get dimensions? And we'll go back to the model tree, and you'll notice that there's an unfold sketch. So we'll highlight that, right click on that, and we'll bring that up in the sketcher. So here's the sketch with all the points, and we also have vertical and horizontal constraints which can be used to figure out dimensions. So the first set of dimensions we'll want is going to be the width of this and the height of this to get the overall dimension. So we'll click this point here, and we'll click this point here, and we'll go up here and we'll select horizontal constraint, and there it is. So we can come down here and just draw this down. So this piece has got to be 197.44 millimeters wide. We can do the same thing for the height. We'll select this point, Control click to select that point and go with a vertical constraint. There it is. Go ahead and move this around. So this part here, I actually made a mistake here, so we can fix that. I should have gone up here, so let's correct that. This is actually how tall this side is going to be, so we really don't want that. So we'll just highlight this, we'll delete it, let's do it again. So we'll highlight this point, and then we'll go all the way up to the top here, highlight that, and a vertical constraint. There it is, that's the number we want. So we'll go back in here now. We want to know what this bend line is, so we've got to pick this point. We've got to pick this point. When you bend this in a press brake, you're going to register this edge against the back gauge, and then your die is going to come down on this bend center. So let's do a horizontal constraint there, and click OK. So there's your bend line. This part is symmetric about its center, so this side here is the same dimension, so we won't bother with that. The next bend line we've got to get is got to be the bend line for this tab. So we got to be careful in here. Let's blow this up a little bit, and we actually want to find this line right here and this line right here. So that's the 2 points there that are going to give us that dimension. So we'll go for a vertical constraint. We'll say OK. Okay, so we can shrink this down a little bit. So that pretty much specifies this part. The other thing that you're going to need to know is what the notch size is going to be. So we already talked about how we can deal with this. So let's take a look at dimensioning out this notch. So we'll go from here to here. That'll be a horizontal constraint. So we've got that, and then we want to know the other dimension, so we'll go from here to here. We'll do a vertical constraint. Kind of pull that down, pull it down here. Put this wherever you want. So this dimension and this dimension is what you're going to notch. This notch and this notch over here are the same size, so we don't have to bother with that. But that pretty much gives you all you need to know to blank this piece out and cut the notches and then do your 3 bends. So we can just close this and come back to our sketch, which we don't really need anymore. So we'll go ahead here and turn the model back on, and we'll go ahead and get an isometric view. There's another little detail that I struggled with that I want to point out, and this is important for the unfold to work. So let's take a look at a right-hand view. We'll blow this up. You'll notice that there's a little tiny space in between this tab and the side of this box, and that's 0.1 millimeters, a very tiny space. And the reason that there's that space in there is the unfold tool has to be able to separate this face from this face in order for its algorithm to work properly. So when you specify the space of this tab and you do it just on the setback on the bend, and this lays right up against here and there's no gap in there, the unfold tool is going to complain. It's not going to work properly. So that changes the flat layout very, very slightly, but it's such a tiny amount that it doesn't really much matter. So I just wanted to make sure that you understand that. The last thing here are these little chamfers, and the lid, when it slides over this box, if this is a sharp corner, the bend that's right here is going to hit that corner, and the box lid or top won't fit properly. So that chamfer is actually specified right here in the chamfer. I usually make it the same as the material thickness, but just for the purpose of this video, let's make it 3 millimeters, let that recompute, go back to the box, and you can see here now that that's increased. Probably 3 millimeters isn't bad, it's not really a problem. And the other thing that's interesting, and it's a very powerful feature, is how you can actually take values from the spreadsheet and use them as parameters in the model. And I'll show you the chamfer here. We go into properties, we go here, and we click on this little formula button, and you can see here how this was done. So you've got left double broken brackets, the word spreadsheet with an uppercase S because it is case sensitive, double right broken brackets, dot, and the spreadsheet cell. And that will bring over the spreadsheet value into the model. which is really, really powerful and very, very helpful. So that's kind of where that value comes from. And if you don't have it set up that way, when you want to change the dimensions and the design of the box, you got to go chasing through all these features, and it's a little inconvenient. So it's best to do that. And like I said before, all of this has been taken care of in the model. You just download the model, it's all squared away. So that's how this model works. They both work the same way, and we can go in to the box top, rotate this a little bit, and let me show you what's going on with the recompute here. So this model here is a little bit more complicated. We'll go into the spreadsheet. There's more values here, and let me explain a few things that might not be obvious. The miter gap is this little space in here, and that's going to relate to the V-notch that you cut out of the flat layout. And you want to make sure that you leave a little bit of space in here so the metal doesn't collide when you bend it and it puckers. And if you make this gap too big, you're going to get a pregnant hole that's going to creep onto the top of the box. So you got to just get that right. So that's what that gap is. The fit allowance is important, and this lid slides over the top of the box, and the fit allowance is the extra width and the extra height that you'd like to see, so this lid or top slides nicely over the bottom. And that's going to be a function of how accurate you blank out your metal and how accurate your bends are. And it might be a good idea to go ahead and fabricate the bottom of the box and take some physical measurements and see how close you are, and then come back and adjust your fit allowance. I used 1/2 millimeter. It's about right, but you might want to use a little bit more if you've got inaccuracies. Now, the calculations automatically take care of material thickness and other things. So these dimensions here, box width, height, depth, and the tab, must match the bottom. They've got to be the exact same numbers, so this will fit properly. So just be aware of that when you use the model. And regarding the recompute, you can see this model's got a lot more faces. It's got a lot of extra things in here. So let's go in and let's make the side, let's bump that up to 15 millimeters. So you can see what's happening here. This is whirly twirly. You can see progress down here. We're waiting. Still not quite done yet. And we're going to wait for another recompute cycle here. And boom, it's done. So if you have got to change 5 or 6 or 7 of these values, you're going to have to suffer through that recompute for every single change that you make. And here's the model. We've increased the sides, and that's kind of how that works. So we'll go ahead and put this back to 12.7. It's a 1/2 inch. And we're going to see this recompute. We're twirling. Progress here again. And we're still not done. So we're just sitting here waiting. And that's that. It's almost done. And this computer that I'm on has got a pretty good processor in it. So there's just a lot of computations that need to be done to deal with that. If you do that, checking skip recomputes, you can go ahead and change all these, and you turn it back on, and then it'll go ahead and go through the recompute, and it's much better. I'd also like to draw your attention to this comment here. No error or range checking is done. So if you put in funky numbers here, you're going to blow up the model. So just be careful to make sure that the dimensions that you put in here make sense. For example, this tab, it's a component tab, has to live within the depth of the box. So this box here is 50.8 millimeters, and if I make this tab greater than 50.8, I'll make it something like 60 millimeters. It's going to get weird. So just be careful that you use some common sense when you're dimensioning these parts. So that's it. I hope you've enjoyed these models. I hope they're helpful. This is a nice little box. You can put electronics in here. You can use this component tab for switch, fuse, lights, grommets to bring wires in. You can also add fasteners on the side. Just make sure that this metal here provides enough so you can drill a hole in here. I used PEM fasteners and 632 screws, machine screws, and it's in the video that shows how this box is actually made. So I've done that, but you've got a variety of options that you can use for the fasteners. So that's it. So thanks for watching, and I hope you enjoyed the commentary.